Welcome to the lecture on earthquakes and plate tectonics. This is not going to be the smoothest thing. I know you're used to that, but in this case, it's not going to happen. Sometimes the perfect is the enemy of the good. In this case, you're just going to get something. Earthquakes, they're not that uncommon. They happen all the time. Here is the National Earthquake Information Center from the USGS, and it shows earthquakes occurring around the world. These are earthquakes in the last 7 days. And you notice they occur in specific patterns. Just thought I'd throw that in. It's kind of neat to know about. Let's get back to the normal thing that you're used to. This is a scene of San Francisco, 1906, right after the San Francisco earthquake. The city was devastated. Now what's interesting is the earthquake didn't destroy the city. The earthquake cracked the water pipes, and it also cracked the gas lines, which then started fires which couldn't be put out by the water pipes. When you hear about the 1906 earthquake, you often hear the great 1906 fire, because that's what destroyed the city. In earthquakes, most people aren't killed by the shaking of the ground. It doesn't chomp them up. It's disease and fire that end up killing them. This is an interesting little sign from a building. If you're in an earthquake zone and you're in an unreinforced building, it could be bad. Now, where are the dangerous earthquake zones in the United States? Well, of course, anywhere along the Ring of Fire. And amazingly enough, right back here along Missouri, Illinois, Kentucky, Tennessee, and Arkansas. The New Madrid Fault, where it looks like our continent is being torn apart, which I think we talked about in an earlier chapter. Here's a cute little thing from the USGS showing the Tohoku earthquake that caused the tsunami on March 11th, 2011. It's hard to tell, but this is the seafloor right here, and there's where the fault line goes underneath Japan. It is an oblique fault that goes way underneath the islands of Japan, the volcanic islands. Here's the fault right here. And this is San Francisco. I thought this was kind of a tragic thing. There are people who go up to the bridge with the intent to commit suicide, and they have a phone there to make a call so you don't do that. And this is what's posted there, at least at one time. Oh, not good. One more recent event, 2010. This is taken along the road down in southern Arizona. There was an earthquake in Mexicali, Mexico, and it started shaking the ground. There were a few landslides, and this is what happened in the mountains there. All kinds of dust started rising from the ground simply due to the seismic activity. This is really kind of cool. Lots of people stopped to take pictures, and I got a hold of these somehow. I would have loved to have seen this. Okay, here is where the earthquake occurred. Right here. Here's Mexicali. Here's the United States, the Mexico border. And here's another view of typical earthquakes. This one was from 2010, February 27th. Notice the Ring of Fire along underneath Asia, along the Mediterranean. Oh, and since I'm colorblind, all these little pink things down here too. I have to look carefully to see those. My bad. One of the largest earthquakes of all time occurred down here near Santiago. They're still occurring right along down there. Here's a typical earthquake list. This is all on one day. It's kind of crazy how many earthquakes occur. When they occur, this kind of thing can happen if your buildings aren't reinforced. Your fences can be messed up. Now, before we start, let's see what you know. Why do earthquakes occur? Do they occur just anywhere? Which type of earthquake waves causes the most damage? Which earthquake scale measures damage? Why do earthquakes tend to occur frequently at shallow depths rather than great depth? What are the two biggest killers in earthquakes? Ooh, I already blew that one. Why do seismic gaps and shadows occur? List 3 quake warning signs. Why does liquefaction occur? And how many earthquakes occur each year? The global distribution of earthquake marks the boundaries of tectonic plates, true or false? And tsunamis are barely detectable in the open ocean, true or false? If I don't remember to come back to this at the end, somebody out there raise your hand and I will come back to it. Earthquakes. It's just a shaking of the ground. caused by a release of energy that's been stored up in the rocks. You know how your mom or dad may get really tense and then they get tense and finally they snap? Well, earthquake is kind of like that. The earth gets tense, then it finally snaps. It lets out waves. I think I'd rather be around an earthquake than an angry parent, though. The whole idea is called the elastic rebound theory, where the crust is distended, it snaps back and sends out the waves. Here you go. Here's a fault. There's pressure being put on this in a shearing motion, but it doesn't let go until right here, and then, well, it lets go. Take a look at this fence in California. Did anybody see my cows? G.K. Gilbert, by the way, is a famous geologist from the old days. Here, fruit orchard. Notice what's happened to the trees right along this fault line here. It doesn't seem like a big deal, but if you have an irrigation canal going through here, this could be a bad thing. And here's where the soft ground has been lifted up. Now, normal motion in an earthquake is 1 to 2 meters maximum. And typically the earth doesn't open and close back up, although recently in the Tohoku, Japan earthquake, you could see little teeny cracks going back and forth. I think I put that in some of the videos. Fascinating. Here is another example of a fence that used to be joined, but it isn't anymore because this is along a fault line. Okay, two types of waves that come from the place where the earthquake occurs. We have the body waves, which go through the body of the earth, and then waves that occur only at the surface waves, which are cleverly named surface waves. Place where the earthquake occurs is called the focus. The point directly above the focus is called the epicenter. If there's a cliff that's formed, it's called a scarp or an escarpment. The line along which you can walk is called the fault trace. And the line that the fault scarp goes along down into the earth is called the fault plane. We just covered all that. Now, body waves. There are P waves, which are compressional waves. They're like sound. Typically, they're about 4 to 7 kilometers a second, and they're the first to get to a recording station. If you've ever played with a slinky, it is this type of motion. You push the slinky and you can send a wave through it, and it can go both directions. You have an expansion called a rarefaction and a compression called a, well, compression. The secondary wave is the S wave, and it's like a rope that does shearing. You could do this with a slinky too. What's interesting is when you send that rope down, it also bounces back, and the same thing happens with secondary waves. They bounce back. Now, P waves can go through solid, liquid, or gas. How do we know they can go through a gas? You're hearing me right now. My voice is going through the air, shaking air molecules, and those air molecules are vibrating your eardrums. Okay, so it has to go through the computer first, but you get the idea. S waves, if I make my hand go up and down, I'm moving air, but you don't hear it. Why? Because shear waves are not propagated through fluids. What are fluids? Anything that moves rather than being still. That includes a gas like air or liquids like water or the outer crust of the earth. So S waves can't go through the outer crust of the earth. They are much slower than P waves. And again, they pass only through solids. Now, surface waves, they are the slowest ones. The love wave, I love that, involves side-to-side motion. Doesn't travel through fluids. That's not good on buildings, but the worst kind of wave are called Rayleigh or Raleigh waves, and that's where the ground actually behaves like the ocean. I was in a big earthquake in the South Pacific once, right along the Tonga Trench, and the ground was rippling. It was kind of cool. My house stood up, so that was good. A tree fell over and smashed a neighbor's house. No, that was a hurricane. Never mind, something else. But these are extremely destructive if you have buildings that can't flex. Now, how do you detect earthquakes? China has a history of earthquakes. They're right along the ring of fire and across the northern part of the Indonesian belt where there are lots of earthquakes. Hundreds of thousands of people have been killed in China. So, people there have studied them for a long time. This is an early seismometer. Frogs, dragons, and something inside. Here's what's inside. This large vase is anchored to the ground. So if the earthquake moves the ground this way, the entire vase moves this way too. The big weight in here stays in place because it has inertia. So if the vase moves this way, and I'm doing this backwards, this thing will swing this way and knock out the ball into the frog's mouth over here. That means that the earthquake will have come from the opposite direction. Yes, the drawing is the opposite of what I'm talking about, but you get the idea. Now, is this very accurate? Well, not too good, because it can tell you, okay, the earthquake came from over here, but it doesn't tell you how far away it is. To identify where it is, you would need a series of these and then send people walking from these in the proper direction until they all met. It would work really well with cell phones, but that's probably not going to happen back 500 years ago when these things were first built. Modern seismometers contain a mass, and when the earth shakes, the mass stays in place. There's a rotating drum here operated by a clock, and you end up writing a seismogram. Let's look at a typical seismogram. Now again, the base and the base moves. The weight stays still, the pin is connected to the weight, and that's the general idea. The first wave is the P wave, then the second wave, then the first surface wave. You may not get a Rayleigh wave depending on the kind of earthquake. Now, in order to get really good earthquake data, you have to have one going this way, one going up and down, and one going back and forth. A three-dimensional XYZ seismometer. Here is a typical seismometer. This is a Mark Products L4 3D seismometer. This is from a little thing that I did at Los Alamos National Laboratory. I was making a manual on how to use these things. And it's all electronic. Everything is inside here. These have to be buried in the ground and anchored really well. They really no longer look quite like this. Here is a Streckheisen. These guys are extremely expensive. I think they were somewhere between $12,000 and $20,000. These then go out to little digital box recorders that are very sturdy. Here's my old boss and a guy from UNM at Socorro putting together a remote seismic array. They're taking this seismometer, sticking it down in here, learning how to anchor it into the ground so that you can monitor earthquakes and yet not have to be at the earthquake in order to pick up this kind of thing. All this stuff will be relayed back to you in your lab. You can just sit there, drink your Dr. Pepper, and have a good time. Now let's take a look. Here's a P wave and an S wave. The P wave arrives at about 160 seconds. The S wave arrives at about 220. So there's a 60-second lag in there. Seismometer's misspelled. Here is a P wave arriving at about 120. It arrives at 180. So which one of these is closer? Here's a 60-second lag. This one is a 60-second lag. The earthquake was equally distant from both of these. Here is a recording of an event in China. Again, working at Los Alamos, these are the data that we get. And I won't say anything else about that. This was an event that occurred in 1997 off of an island north of the old Russia/Soviet Union. It was curious because nobody knew if it was an illegal nuclear test or an earthquake. How can you tell the difference between them? Here's a typical earthquake. It builds up. A nuclear test, it's one event that then kind of peters out. Let's pause here and we'll pick it up on the other side.